In this video, I'm going to show you how to calculate the p-values for the Fisher-Hayter q-tests that you may have calculated based on the procedure I described in a previous video. So what you need is you need to make reference to the q distribution with the following function in SPSS. This is at least one way to do it. And basically it's the CDFS range distribution, which you then specify the q value, the degrees of freedom in the numerator, which is equal to k minus 1 of the groups, and the degrees of freedom in the denominator, which is associated with the mean square error. And so in this case here, we can see that the mean square error is equal to 348. So those are the degrees of freedom that we're going to put here. And in terms of the degrees of freedom in the numerator, it's actually 3. So that's an advantage of the Fisher-Hayter, is that it's using k minus 1 as the degrees of freedom in the numerator. And of course the q value would be something that you calculated with this Excel sheet if you chose to do so. So let's say we tested this q value for statistical significance, where we have the federal agents, it's sample size 84 versus sample size 36. So it's federal judges versus police officers. So we're going to test this corresponding q value for statistical significance. And so because there were a total of 4 groups in the analysis, we'll actually specify 4 and the degrees of freedom associated with the mean square within, which was 348. So once you go into SPSS, you'll have to go into the transform utility is one way to do it. And we're going to call this p-value. And what we need to type in here is 1 minus CDF range, 1 minus CDFS range, 1 minus CDFS range. Yep. And we need the q value that we calculated, which is 5.191. Five 0.191. 3 decimal places is the minimum I'd recommend. And we've got 4 in the numerator, and we have 3 in the numerator and 348. 3 and 348. And so this function, when I run it in SPSS, is going to give me a p-value for this q value, because it's going to call the q distribution, if you will. So click on OK. And here is the result. It's giving me a p-value of 0.008. I could actually show it here. 0.008161. And of course, it's the same for all of them. It's actually just calculating the same p-value across all cases here, but the key point is you look at this value here and it's less than 0.05, and therefore you would reject the null hypothesis. Now, I report in the textbook the values associated with the Tukey-Kramer HSD for all the comparisons, federal agent versus federal judge, where the q was equal to 4.316 and the p-value was equal to 0.013 for the Tukey-Kramer HSD. And the Fisher-Hayter is equal to 0.007. And I mentioned in the textbook that the Tukey-Kramer HSD, better known as just the Tukey's test, is more conservative than the Fisher-Hayter test. And that's why I recommend that you use the Fisher-Hayter test, because the Fisher-Hayter test is not only not as conservative, it still simultaneously keeps the family-wise error rate close to 0.05 for the entire family of the analyses. 0.008 for that one. And you can see that the p-value I reported was 0.001 for the federal judges versus police officers, which in rounded terms is the case. I just rounded p-value of 0.0008, I rounded to 0.001. So that's how you can do an estimate of the p-value for a q statistic derived from the Fisher-Hayter q-test, which I recommend that you use if you can take the time to actually conduct it.